Bonsoir à tous, merci beaucoup d'être venus ce soir. On va commencer la présentation, on va commencer avec Group Cutting qui va nous présenter les activités de Cloudera. François va faire une petite introduction sur vidéo et on le remercie chaleureusement pour son accueil. Ensuite, les présentations de Cassandra et MapR. Et ensuite, petit cocktail comme d'habitude.
Should I speak English or French? Okay, I'll do that in English. Well, first, we're very pleased to welcome you tonight at Viadeo. I don't know how many of you know Viadeo already. Raise your hands. I thought so many. Okay, so Viadeo is, in a few words, quickly, professional social. Was born in 2005, born in France actually. Now Viadeo has a global presence in China, Russia, India, Europe obviously, and Africa for instance. So it's not only that French company that does a French social network, professional social network, it's really a global PSN. So we have about 50 million members. So 15 million members is a lot of things happening on the website. People connecting, exchanging messages, publishing, sharing news content, articles. You might have a number of interactions. Basically, that translates into a lot of data. So we have in your typical big data setup. So the idea is to cope with this huge amount of data that flows in the system and flows out, actually. We have a pretty dense technological stack. I mean, not dense, diverse. So we use Hadoop, obviously. We use HBase, Elasticsearch for the search auto-suggest list, for instance. We use MySQL for the transactional database that are piping the website. We use some queuing systems such as RabbitMQ, some storm processing to work on indexes, MongoDB as well, and then the applicative part we do in some part the Spring J2E, okay, and on the CRM part I'm actually directing the team, brand new CRM system, event-driven, real-time, mission-critical system. And that is based on the Play framework, in a specifically in the Scala language. And we actually plug that to HBase as well, and HDFS, and we do a lot of, getting started with scalding as a DSL to crunch data, to do our MapReduce jobs. So that's a quick overview of our tech stack. The teams are growing, so if you're interested at some point to discuss further or be part of the adventure, don't hesitate to talk to us, talk to me. That's it. So now, on with Doug, I suppose.
Thank you.
So I don't have any slides. I thought it would be better to just talk. I'll spend a few minutes sort of giving an outline of the sort of things I've been thinking about recently and where I think what I think the state of the Hadoop world is, and then I'd like to answer a lot of questions, find out what you think. It's easy to find presentations by me and others about various things, but it's I think that hopefully the opportunity is here to learn what you care about. See if I can help you in any way. First I want to go over sort of the origins of Hadoop and where I think it's going. I think we've developed into a platform. I want to apologize for my voice. I'm sorry. I have a cold. It doesn't normally sound like this. But it's developing into a platform that is really becoming the primary platform, I'd say, for data. I think big data is becoming just data in enterprises, which is not something that I planned, I think, or expected. And it's kind of surprising. It's interesting to think about how this has come about. I think there's some trends that have led to this. So we have obviously the hardware trends, which are phenomenal. We've seen hardware get cheaper and bigger and faster at exponential rates for 30 years, 40 years, a long time of our lives. We've had this exponential growth. And I think what we're sort of at is a phase transition in what are the ways we can organize our technology, the way we can use this. In parallel, as hardware has gotten less expensive and more plentiful, we've seen it get adopted by industries. I read somewhere recently that if you look at the industries that are growing fastest, there's a pretty clear correlation between those that are adopting technology. The more you adopt technology, the faster you're growing as a sector. And if you're using technology, you're generating data. You may not be saving it, but data is passing through your systems. And I think what the big data trend in a nutshell is, it's just the realization that if you generate this data, you can save it, you can afford to save it. It's now cheap enough. These economies of hardware permit us to save it. And all we need is some software that is equivalently economical and it scales to use all this inexpensive hardware and lets you process this data. And Hadoop happened to be the first instance of such software that came along. Obviously, one of the keys to its affordability is open source. People have learned through the last few decades that if you keep your data in software that someone controls very tightly and that you have to pay for on an annual basis, on a recurring basis, then the price may go up. And you may be forced to spend more because it may be not a good way to move your data. You get locked in, and it becomes a dominant cost. Another trend of the old ways of doing things was using very exotic hardware, and these very centralized architecture, centralized storage, centralized processing, and that again doesn't scale very well to the sorts of economical hardware that's produced en masse. So anyway, we've seen these trends combine, and we have this phenomenon. And I think if you look at each of these trends, they're not things that are about to stop. Some argue that Moore's law may slow. It's not going to stop altogether, I don't think, anytime soon. And people have been predicting it's going to slow for as long as there's been Moore's law, and it hasn't slowed much yet. So I think it's safe to assume that will continue. And even if it doesn't, the adoption of technology by industries around an early stage, there's lots of room there. And so the rate that the amount of data is growing is super exponential. So I don't think there's much risk of this being a hype bubble fundamentally. I mean, there may be some elements of hype around in how companies are valued or things like that. But I think the fundamental technological trend is pretty solid. And so if you're thinking of investing in it, I think you're pretty safe. Another thing that's surprised me tremendously, I started out with Hadoop about 7 years ago. I guess we took it and split it out of Nudge. And I fully expected there to be some serious major competitors. And I have to say that really hasn't transpired. I thought that Oracle and IBM Microsoft would each come up with their own sort of equivalent systems. And each of those companies, I think, probably had equivalent systems internally. But they pretty much, down the line, elected to start using Hadoop. And so it's become the standard for these sorts of things. It's also changed, I think, over the years, what sort of a system Hadoop is. We started out, I come from a text search background, worked writing search engines with Apple and Excite before I wrote Lucene, which you may have heard of. So I was sort of accustomed to doing things on flat files, not building things using relational databases. We tried that multiple times to do search that way. It didn't really work. And we've really sort of established a new way of building distributed systems. But there was initially very much a sort of a batch-based system in Hadoop. We had the MapR and we had not really any interactive systems. Lucene was interactive, but it didn't really live in this distributed world. In the years since then, we've seen a lot of interactive capabilities added to this platform. HBase was an early one. Then last fall, Cloudera launched its Impala project, doing SQL queries interactively. Now with Solar, you can do scalable search using Lucene underneath it. And Cloudera has just announced an integration of Solar living inside of HDFS, using all of all the ecosystem, so you can have events flowing in from Flume and Index with the help of NG data friends, index things into HBase, and have it be fully integrated in with this platform. We saw also last fall a paper from Google, which was pretty stunning to me, where they talked about, this is the Spanner paper, doing transactions over distributed databases that are spread across the globe. So this was something that I think people thought we couldn't really do. If you looked at maybe 5 years ago, people talking about these sort of big data systems, they'd say, well, you can't really do joins in these distributed systems, and you can't do transactions, but that's okay. We can build our systems without those, and we'll learn to engineer around those deficits. And now we're starting to see things which are able to do join transactions. Now, not all these capabilities are yet in the Hadoop ecosystem, but I think they will be there shortly. So it's really become sort of an operating system with the sort of capabilities you expect in an operating system of authentication, resource management, process control, all these kinds of things. Very general purpose, but a distributed operating system for processing data, and becoming the standard operating system in the way that Linux has on individual machines in most places. So I'm trying to think if there's other things I want to add before I hear what you want to say. I think that's mostly what I was going to say. I was also going to add that it's in what Google has done here. If you look at these history of technologies, they've shown us what was possible through these papers repeated times. That Hadoop came from the GFS and MapR papers. HBase came out of the Big Table paper, and so on. Pig and Hive were inspired by various papers from Google, or at least preceded by those. So people knew that was possible. Impala is inspired by work from Google. And so when we see new things come out, we know that we have a sort of an analogous universe to Google's. But a few years in the past, they can tell us where things lie in our future in many ways. So it's fascinating to watch how they progress and how they're now able to do, for example, global transactions, and they've replaced all of their MySQL and ad sales is what they're using Spanner for with Spanner. Anyway, that's sort of a brief overview of the way I see the world today here. And I'd like to hear what folks here think and open it up to questions. I think we've got probably 15 minutes or more in my time slot. So we should be able to get a lot. I'm here on my vacation, so no hard questions. And if you have fun questions, that's better. Everybody? Don't be shy. There are no dumb questions. Must be something you want to ask me, or ask the room.
Why is the elephant yellow?
What's that? Why is the elephant yellow? So the elephant was a gift that a friend of mine gave to my son. And she decided to, and my son played with it for many years, and during those years he named it Hadoop. During those years also the label wore off. So we have no idea who made the elephant. I've never been able to find out who the manufacturer was. I know the woman who owns the store where he bought the elephant, and she can't remember where she got the elephant. I spent some time trying to figure this out, but he was yellow. And when I heard my son say his name, he was calling the elephant Hadoop, I knew one thing. I couldn't ask him why, because he's 2 years old, and you can't ask a 2-year-old why. Or you can, but you won't get anywhere. But I also thought, yellow elephant, 6-letter word, easy to pronounce. It's a perfect software project. We've got a mascot, we've got a logo. I just sort of set that on the shelf, and it was probably 4 years later when the project started. Taking this part out of the notch, what are we going to call it? Right here, and it seems to have done well. But anyway, it's fun to see it on the wall here. I'm glad my son didn't come tonight. He's in an apartment here in Paris. It would go straight to his head. He would say, "See, Dad? See, it's all me."
You have operations in France, or do you plan to build an office in France?
The question is, does Cloudera have operations in France? We don't have an office in France yet. We just opened an office in London, which is meant to be our European headquarters. And so we're really, this year, starting to establish operations in Europe in general. I don't know how long it'll be before we open an office in Paris. I don't know what the order that we'll try to spread things around. In the US, we have 5 offices right now. We've got an office in Tokyo, and we've got one in London. That's sort of where things are this year. So I'm going to probably come back in September, since we're trying to ramp up efforts here and visit more people and get things going. We have some customers already in the UK. I think it's the reason we started with London. I think the New York office had gotten started with some banks that are headquartered in the UK but have offices in London, in New York. So soon, we should have people on the ground in France. Anything else? You can shout it. There we go. About which? Impala? Uh-huh.
I'm asking another question. Isn't it the role of HBase
Steven's saying, don't refer to me. So is it realistic to have real-time SQL? Well, I'm not sure what real-time means. Depending on the size of the database and the complexity of the query, some things are going to take longer. There aren't a lot of shortcuts. Unless you can build a bigger cluster. You sort of have these you can scale things out by distributing things more. I think, as far as I know, the distributed database algorithms scale pretty well. I think most people are finding that most of their Impala queries return in a small number of seconds, or under a second for a lot of things, on in a reasonably well. Is that real time? No, it's not the sort of time you might want to put behind a page view, probably, where you might want to have it more like 100 milliseconds or so for data access time. HBase is there today for those sort of lookups. But we'll see. I mean, we might hopefully performance will get better. I think performance, if you're talking to Impala data that's entirely in memory, then I think, and for large classes of queries, I think you can get down to that 100 millisecond sort of range. It's certainly designed to be able to do that. But there are also going to be queries that you can't do that. So there's a lot of variables there. So I'd have to say it depends. And you're asking, isn't that the role for HBase? I mean, HBase is fundamentally a key value store. It's well suited for those sort of loads. But in terms of complex queries, there are people who are working on building SQL on top of HBase, and that will be integrated directly on top of HBase. And we'll see how that goes. And also there's work to get Impala to work better on top of HBase as an SQL engine. Depending on your needs, size of your data, size of your cluster, it's there today, or it may be there, or it may never be there. Very clear answer, right? What you want? Yeah. Yes.
So is it just configuration of
So I mentioned ngData when I talked about search. So what ngData has done is helped us with the integration between HBase and search, so that things can be indexed. I believe the way it's data now builds on top of Cloudera search to a large degree, and then becomes a component in Cloudera search. At least a component of ngData's products is going to come. With the search, we really are. It's not a lot of new code. There's some new code, obviously. Most of the new code are things that are going to get pushed upstream into various projects. There's not a lot of code that's really going. There's not a big Cloudera search open source project. Rather, there's a directory implementation, a Lucene directory, if you're familiar with that, the Lucene storage backend abstraction that's implemented on top of HDFS. That's very efficient. And so we want to push that up into Lucene. There's connectors for Flume, which we'd like to push into Flume, and so on. We want to mostly have this all just be stuff that's in the various projects. It's mostly integrating various things, but there were little bits of code that needed to be written to make all these things work together well. If you look at the amount of code that's involved when you're running it, it's 98% is existing open source projects, and then it's the last 2% of gluing them all together. I think a big change. I think previously people haven't stored Lucene indexes in HDFS, and years ago we tried it, and it was very slow. And people said it'd be nice, it'd be convenient, but it's too slow. And so everyone's always done indexing to the local disk. So we tried storing Lucene indexes in a relational database. We'll try storing exploits and always found, well, they need to be in the local disk or in memory. You get good performance. And Aaron McCurry, who's working on the Blur project, he's not associated with it, came up with this Blur search engine built on top of Lucene, which actually very efficiently searched. And it was just nobody had to really try building a little bit of caching, was all it took. If you're talking about the local file system, everything depends on a certain amount of caching, certain cache semantics. And with HDFS doesn't do any caching in the client. And if you add a little cache in front, then you get performance that's as good as using a local file system for indexing. It was that simple. So we borrowed that code from Blur, and worked with Aaron, and I think we're going to probably move it into Lucene so that we can all share it there.
Hadoop is really changing the things you do on the energy market. How far do you believe you can hit the big reference like the Cloudera or
Right now, I'm pretty optimistic, pretty far. We'll see. I mean, I think at Cloudera, certainly, what we see ourselves as being more like a Red Hat. We're providing this platform, and want there to be lots of applications that build on the platform and can share it, and that it can be the way that the standard way that everything can be deployed and work together well. So I think we're seeing more and more existing vendors move to integrate better with the Hadoop platform. There's some patterns you see there, some that I think are good and some that I think are not so good. For me, the sort of test of whether somebody gets it, gets Hadoop and how to work with it, is the degree to which they can keep their data in Hadoop and not have to move it running two different systems. So if it's nice that HBase's data lives in HDFS because if you've got disaster recovery, you've got authentication, you've got various administrative things, you can share all that. You can share the allocation space on your hard drives. Moreover, you share your switches, and your data can move very easily between things. Same thing with the search. We felt it was very important to get the indexes into HDFS. And Paula will search with SQL queries your basic sequence files of the sort of standard files that are in HDFS already. You don't have to do a big load phase. So I think things that either take data and move it entirely out of HDFS are to process, and then you have to move it back, are mistakes because moving data is very expensive. And something else. But yeah, so I think that's a pattern to look for when you're evaluating things, is to see how natively they're able to integrate with this platform. I think is an indicator of how well they're going to survive in the coming years. In my opinion. I may be wrong. Yeah.
A few weeks ago, during a meeting, I have talked about Hadoop and big data, and a lot of people thought that Hadoop is only for social network companies like Facebook. So, my question is, how can we move the image of Hadoop and big data from social to an image of a natural project for big business?
Well, there's a lot of companies that are using it for things besides social networks. So you can find references. It's a good way to convince people. We've got, in the US, the biggest credit card companies put every transaction into Hadoop and use it for fraud prediction. Chevron Oil uses it to analyze these undersea sonar data. They get these tuples, which are GPS coordinates and a timestamp. I think that's that simple of when a ping was heard. Maybe they have, I don't know, maybe they have a ping ID or something. Very simple little tuples. And with that, because they have a boat, they pull a bunch of microphones at one place on the surface, they bounce off the bottom and the undersea, and they can then analyze everything that's under the sea and find oil by a lot of intensive analysis over these data sets, and they're using Hadoop for that now. You got banks, you got medical company. Anyway, if you want, I can send you a list of big company names who are starting to use this stuff. Most companies are using it in a few places. They're not using it across for all their data sets. But I think, we talk about like the Fortune 100. I think half of the Fortune 100 are Cloudera customers at this point. And so there's probably some more of those who are using Hadoop who aren't in the, but aren't Cloudera customers. So you could say that the vast majority of big companies are already using it in some capacity. So it's hard to argue that the Fortune 100 is all social networking companies. But I understand that it's it started out there. Facebook was a big early adopter, but there's a lot of others. There's the biggest consumer electronics company in the world uses it for every transaction that comes through. There's massive things out there. Some customers were not allowed to. They don't let us say their names, but there's also pretty impressive ones that do. The biggest retailers in the country, every transaction they do in their stores goes into Hadoop, and they analyze things there. So it's real. Somebody told me yesterday that French companies aren't persuaded by American companies using technology. They need to hear about French. That may be a chicken and egg problem. It will take some companies being more adventurous. But I think that will happen. You get some startups who become bigger, and people see who aren't in social networking.
Maybe one last question, and then we'll continue afterwards.
Sure.
Yeah, one question to Twitter. I've got any future plan for cluster discovery.
For which?
Cluster discovery.
Future plans for cluster discovery. I'm not sure what they mean.
It's through Twitter, so.
Does anybody have an idea what they mean? All right. I'm sorry.
Second last question.
Right.
I hope this isn't I hope it doesn't come across the wrong way, but when I first started using CDH3, and that was basically because the Apache Hadoop project was kind of left for dead in some ways, and important ones came along. How does Cloudera's strategy change, and do you ever see them merging back together as far as open source distribution? Because I know, at least in the CDH3 days, there was a number of patches that was added on top of the 0.20.2 or whatever, and I think that's grown in CDH4 to some extent.
Yeah, it's got a lot smaller in CDH4.
Really? Oh, okay.
There was a fork that Yahoo maintained outside of Apache for quite a few years there that had a lot of important stuff in it. And so we were merging a lot of that in CDH3. In CDH4, there's fewer patches. There's still patches. Every patch that we put in is always contributed to Apache, and I think almost always committed and at Apache before it goes into a CDH release. CDH is entirely open source. All the changes we make, we push upstream back into the projects. And in terms of the other distributions, I think we're actually all getting much closer. There's decreased fragmentation. There's a big top project, which is kind of like Debian for Hadoop. But there's only one big top project. In the Linux world, you've got multiple package managers and systems. And I think pretty much everyone is, all of the various distributions are building off of big top to one degree or another. So that gives you some sort of standard way of testing the integrations between things. And so big top is an Apache project, and every Cloudera release starts with a big top, and then we add patches from there to get more stability, and also just to make it, we promise our customers some number of years, and the open source project tends to move along and not keep patching and backporting all the bugs and so on.
Thank you very much.
Thank you all.
Okay, so good afternoon, everyone. I came from DataStax. My name is Piotr Kołaczkowski. I work for DataStax as a software engineer, as a programmer. Actually, I live in Warsaw, in Poland. I'm working from the world. As you may probably know, DataStax is a US-based company. We got this in San Mateo, California. And what we make, we are building a product on top of Apache Cassandra, which you of course know as an open source project, very well known. And today I'd like to tell you how we integrated Hadoop with Cassandra. We got more technologies in our stack. Of course, Doug mentioned search. Yeah, so we've got also a solution for search. We integrated Solar, but I'm not going to talk about it too much today. And yeah, so we are doing what probably many other NoSQL companies are doing. I mean, they are integrating some technologies over Hadoop. And okay, so let's get to the point. What are the options if you want to use both Cassandra and Hadoop? For example, imagine you've got a running Cassandra cluster, this on the left, and you also got a running Hadoop cluster somewhere installed. So integrating those two things so that you could run your Hadoop MapReduce jobs on top of Cassandra using the data that are in Cassandra is pretty straightforward. In Cassandra, in the open source version, in the version you do not have to pay any license fees or so, it's just grab it from the internet. We deliver so-called column family input format and column family output format. Those are the classes that allow you to read data from Cassandra and write data back to Cassandra in a Hadoop compatible way. So, okay, how it looks like. For example, you've got a table like this on this slide. Cassandra is a column family-based store, so it's similar to Google Big Table from the storage perspective. So every node stores can store a table that has wide rows. So we can put, for example, 2 gigabytes of data into one row. The schema is very flexible. You've got every row can have a different set of columns if you wish. Okay, and this is mapped to, this has to be mapped somehow into Hadoop keys and values, yeah, because keys and values are the things that MapReduce jobs are operating on, your mappers and your reducers. So the column family input format extends input format where key is a just byte buffer, which will be your keys from the table you're operating on. And the value is actually a sorted map of columns in a single row. So when, for example, you write a MapR and you want to process your table in Cassandra, what that column family input format would do, it would, of course, split the table into separate splits, so they can be processed separately by multiple mappers in parallel on multiple nodes. And the record reader that is produced by that column family input format would give you one at a time your row key and the whole row with all the columns and all the column values. This is a good option if your rows are not too big, because if your rows are big, the whole row must fit into memory, yeah. So this wouldn't work very well. But for small rows, it's the desired solution. So this works like that, and it iterates your table in the order how it's stored in Cassandra. Okay, we've got another mode of operation in the column family format, because yeah, we also must somehow support very wide rows, for example, like several hundred megabytes, several 100,000 columns. So this special wide row support is turned on just by the job configuration option. And then the keys and values are the same data type in Java. But what is you get at the input key by buffer, you get the row key, but the value you get only one column at a time. So it will go like that, horizontal. When it reaches the end of the row, it will jump to the next row, and so on. This has the obvious benefit that it doesn't load the full row into memory, just a single column. Actually, below it does that in batches. So it's also known that our internal implementation fetches one column at a time, because that would be very inefficient. Because you get the whole lot of overhead for just fetching a column. So you can specify also options how many columns are fetched in one batch. Usually it's something over 100, but you shouldn't specify too much in order not to exhaust the memory. It can also play on the whole table, but you can limit your working data set by specifying some filtering expressions, and those expressions can use Cassandra secondary indexes. So if you index some column, for example, here you have indexed column car, you can very quickly find only the rows that are matching some car. This is a hash index, so only equality comparisons are supported for now. I mean, you can add inequality comparisons, lower than or greater than, but only as a secondary or as a second or third clause to the expression. So the expression must have at least one equality clause that is referencing the index. And then, well, instead of filtering that in the MapR or in the reducer, in the MapR actually, the Cassandra would do the filtering much more efficiently by using secondary index. Okay, so when you process your data, you sometimes want to also write your data back into Cassandra or modify existing data in Cassandra. There are also two options right now here. These are all options that are supported in the open source Cassandra project. There's column family output format, which works in a very similar way. I mean, the key is just the row key of the Cassandra table, column family. And the value is a list of mutations. You have to produce that in your MapR or in your reducer. This column family record writer will queue all the mutations you're producing and send them to the client, the thread client, that will then use the standard thread supported by Cassandra to stream those modifications and data mutations into Cassandra cluster. It has a nice property that even during the streaming, one of the Cassandra nodes fails, it can transparently switch to. Here's a simple example. I mean, that is not very long code. Yeah, this is the part of the code you have to place in, for example, in your reducer. And, so here this code just adds a column, the row with key car. One important thing to note, maybe that's not very obvious, in Cassandra, insertions and modifications are actually the same. I mean, Cassandra is an append-only data store, so when you add under the same row key column name, a different value, it just works like overwriting. And if you add a new column name, then it will be inserted. You also can delete data in a very similar way by using the same thing. Okay, this is not a very fast way of doing it, but this is very flexible, yeah, because it works just with whatever faster uses the public Cassandra API. There's also, well, a hack which allows you to generate the Cassandra data files immediately by bypassing all the networking, all the thread overhead. So this is much faster, but it requires a little more work from the administrator, from the owner of the MapR task. So this is bulk record writer, which serializes all the writes into a memory buffer. And when that memory buffer fills in, and then it is flashed and as a stable, which is placed in the Hadoop temporary directory. and then you can just put those files into Cassandra storage directory, and here you have your data. Yeah, so then you can use it from Cassandra. This is a little hack, but it's much faster. So I also recommend using that if you have a very huge amount of data. Okay, so this is the very basic option what we have if you go with the open source Apache Cassandra. But we here in DataStax, we integrated it a little more, so it's much more convenient for users. As Dax said, it's not a very good way to work with Hadoop when you are moving too much data around. Yeah, so fetching data from Hadoop, getting it into Cassandra and packet. This is not very efficient. So we at DataStax Enterprise, we've got a solution that uses Cassandra replication actually to the data moving when they are first written to your cluster. And in the same cluster, you'll have both Hadoop nodes and real-time Cassandra nodes. This may be a little misleading because those analytic Hadoop nodes here, they are also running Cassandra. This is like more Cassandra plus Hadoop versus pure Cassandra nodes. So Cassandra will do the replication, replicate the data into all the nodes in the cluster, both the analytic ones, the Hadoop ones, and the real-time ones. And when you run your Hadoop MapReduce job, your data are already there, and the job will be run on the analytic nodes only. So you've got, as a bonus, you've got a workload separation feature. So when you run very heavy MapReduce job, it won't affect your real-time job. So the Cassandra nodes, they don't get any requests. Another important feature of that is that there is actually no single point of failure, I mean, even not a temporary one, because this architecture does not require you to set up the whole Hadoop distribution as with Cloudera or with open source, the Apache one. You don't have to configure data nodes, name nodes, zookeeper, all those things. This is simply not here. We replaced it. In the basic solution, you have to do that. You have to install whatever open source or whatever Hadoop distribution you have to make it work. But here, it comes well, as a single package, and I show you how it's actually done later. But before that, because it comes as a simplified single component, every node is actually the same software. The Hadoop nodes are actually just the DSC nodes, but they have a small option turned on that you just tell them that, okay, I want to run Hadoop on that node, so please start job tracker and task trackers for me, and register that these nodes are Hadoop ones. So that is all, but the whole data stack, I mean, the data storage, the replication system, it's the same. It's just done by Cassandra. It's not only Hadoop, as you can see here. This is the screenshot from our Ops Center console. This is a web console for administering DataStax Enterprise clusters. And you can also see here that not only pure Cassandra, pure nodes were playing 3-in-1 ones, and you've got also Hadoop nodes with the Elephant, and you've got also search nodes, and this with the magnifying glass. So this concept was also applied to Solar, to search. If you don't want to use a graphic web console, there is also administrative console from command line, and you can see here that actually what Cassandra does, it places the analytic nodes into separate logical data center. Cassandra has a notion of multiple data centers. It supports multiple data centers natively. So this feature was used to place the analytic nodes and also the search nodes into separate data centers, so that you can separate them very easily easily separate going into those parts of the clusters. Of course, physically, it doesn't have to be a separate data center. It can be still one data center in, well, just one room. Okay, so how we did that actually, because I told you that we will replace some parts of Hadoop. So what we replaced actually HDFS. There's no HDFS in DataStax Enterprise solution. We replaced it with CFS, which stands for Cassandra file system. And the Cassandra file system is a thin layer on top of Cassandra that allows you to store files directly in the Cassandra storage. And Cassandra file system offers the same API as HDFS. So all the Hadoop tools that use HDFS, rely on HDFS, can work with that. I even heard such a crazy idea, just asked us whether we have HBase running on top of Cassandra. Which I thought, well, just a crazy idea, yeah? Well, why would you want to do that? But yeah, I think that's, well, maybe it would be possible, yeah, probably, because HBase runs on top of HDFS, yeah, so theoretically, who knows? Okay, so Cassandra file system has quite different properties from HDFS because it's fully decentralized. And there's no single, well, name node or something like that that you have to communicate to get access to your file system. You can talk to just whatever cluster node, whatever Cassandra node to get your files. This also poses some small problems for us. For example, we noticed just recently that this means that you're going to have separate Cassandra file system URLs pointing to the system, and this sometimes confuses some Hadoop tools because there's no single point, especially in Hive. But this is a minor technical issue. It is replicated. It's replicated by Cassandra. So we also decided that, okay, why duplicate what is okay? Cassandra is very good at replicating things. It has a very flexible replication model. You can set your consistency levels. You can set your replication factors. You can have your data center support. Yes, so you can have different replication factors in different data centers. So why duplicate that with adding another HDFS component, which does mostly the same? I mean, the purpose is very similar. Why not reuse what was already in Cassandra? So that's why it's done like that. Additionally, it's compressed with a snap compressor. It's flexible. You can control which files, which directories in your file system are compressed. Because if you are storing zip files, maybe you don't want to compress them another time because it wouldn't work anyway. And here's the example from using the standard Hadoop. Actually, we use standard Hadoop jars to access the file system. Yeah? So we just point Hadoop to the different URL. We point it's to a different file system implementation class, and the rest is standard Hadoop. It works. The CFS architecture. Okay, so how the files are stored actually in Cassandra. Of course, files are stored in big blocks. However, Cassandra is not very efficient in storing very huge blocks, like for example 128 megabytes. This might be a typical size of a block in Hadoop. So if you wanted to store such blocks directly in Cassandra, you would get into some latency problems. It would work, but the latency of getting such a big blob from Cassandra would be high, and it also would consume quite a lot of memory. So we decided to split it into smaller sub-blocks. Sub-blocks are around 2 megabytes, and such a small 2 megabyte sub-block is quite fast to fetch and doesn't use much memory. There is a separate key space for storing the keynotes, so the information about the paths and the mapping from paths to the list of blocks, and then list of subblocks. As you can see, the blocks are stored as physical rows. I mean, so one block is one row. So it is a nice example of how our wide row thing works. we had to modify one thing in past, because Cassandra is so-called size-tired compaction, so it's probably also the same, it's very similar in all the Google Big Table related systems, because it's probably from Google. So the problem with size-tired compaction is that it tries to merge first the most recent S tables. When it merges, for example, 4, and it creates a bigger one, then it merges another 4, creates a bigger, and then the problem is with Hadoop MapReduce jobs that they're producing often many temporary files, very big files sometimes, but they are temporary. You run the MapReduce job, the files are there, stored in the file system, in the distributed file system, and afterwards you start another job, but you don't need the previous files. And if you would leave the Cassandra, the time until those files would be actually deleted, it would be quite large. And Cassandra would do lots of overhead, a lot of needless work, just to realize that those blocks are not used. So we replaced that compaction, and we use a special Cassandra file system compaction that works in a slightly different way. For example, imagine you've got two S tables which store some blocks, and then a new S table counts. When in that S table there's a tombstone for block 1 and tombstone for block 2. Tombstone is just a deletion marker that I don't need that first block and second block anymore. So this CFS compaction module tracks which blocks are deleted and marks them. Near every S table, there is just a separate file that shows the list of deleted keys. When another one comes and it deleted block 3 and 4, now we can see that the first S table with block 1, 2, and 3 can be just deleted. So we don't need to compact it, we don't need to read it and merge it with some other S table. We just delete the file from this, which is much faster. Okay, so this is just about CFS. We've got also Hive integration, we've got MapR integration, we've got Big integration. Because, okay, if you've got working Hadoop, it was pretty straightforward, yeah, to just put Hive and Big and MapR on top of that. For Hive, we also did some integration components. One is Cassandra Hive metastore, because standard Hive lets you store the metadata in the relational database system. It comes with embedded Derby database. You can also use Postgres or some other database. But okay, we've got already a database, Cassandra. So why not put those data into Cassandra? So we wrote the Cassandra Hive metastore. It stores the Hive database metadata in Cassandra. It just serializes the objects there. This also simplifies maintenance. Yeah, you don't need another database engine. Cassandra storage handler is of course an optional thing. If you want to create Hive tables, Hive external tables that fetch your data directly from the Cassandra tables. And then you just use the Cassandra storage handler, and it can both create new tables in Cassandra, so you can output into that and write data, but it also can automatically map existing Cassandra tables into a Hive relational model. So it's very flexible. Here, a very simple example. Imagine you have a key space matrix, and there you've got a my Hive table. Inside that, in the Cassandra model, so you Hive just use this statement, create external table, you give that it should be stored by our Cassandra storage handler, and then Cassandra storage handler would just go to Cassandra and figure out all the mappings by just looking at the column names. And after this simple statement, you just can query your table as if it was just, internal Hive table. It starts a MapReduce job on your Cassandra data. It uses that column family input format I mentioned at the beginning of the presentation. If you don't like the default mappings, it just maps by name. You can, of course, configure it, customize it. Yeah, so there are lots of properties. You can also customize the size of the split, how many splits should be produced from a single table. You can also customize how input format, in which mode it's run, whether it's in the standard mode or it's in the wide loop mode. Yeah, so it also supports wide loops. Okay, so that's all what I got prepared for today. Any questions?
One question maybe. So what is a typical business application where Cassandra is required versus another NoSQL database?
A typical application of Cassandra is when you need very fast real-time, very fast real-time key value store. I mean, that's again more about business cases. Would probably Jeremy describe more use cases with Cassandra and Hadoop, but Cassandra is very focused on the real-time part. We are not focused on very much on the analytical part. So it can do simple queries by primary key, very fast, very excellent performance of writes, excellent flexibility related to consistency levels, availability, excellent, very high availability. It's decentralized, yeah. So you don't have even temporary single point of failure. You don't rely on failover, yeah. So we don't need to detect that some component of your cluster failed to switch to another one. So there's no downtime. Yeah. So these are the strong features of Cassandra. Many customers already have Cassandra, and sometimes they need to. Well, okay, we got that great real-time system, but we want to analyze those data in Hadoop. So this is a solution for that. It's not like we are trying, well, to somehow make Cassandra an analytic solution. Its primary purpose is real-time.
Can you say what you mean by real-time? Is it on the order of second, 100 milliseconds, 10 milliseconds?
It's usually below 10 milliseconds. It's in order of single milliseconds.
No any benchmark comparing HBase?
Any benchmarks compared to what?
HDFS and CFS.
Benchmarks comparing HDFS and CFS, we haven't run benchmarks dedicated to just HDFS and CFS layer, but we ran some benchmarks with MapReduce job, for example, TerraSort. And I can say that it very much depends on configuration, but sometimes it's like we are 20% faster, sometimes it's like Cloudera's 10% or 20% faster. It's most of the time tied. Yeah? So there are no significant, very huge.
Are you using a binary protocol or
Interrupt binary. Yeah.
Are you wondering about the new native protocol? The more recent Cassandra version? So currently, it uses the Thrift interface, but work is being done right now to support all the different constructs of the native protocol. So that work there's work being done on that right now, but it's not currently supported yet since it's so new to the native protocol.
So there is a work in progress. So the integration between Hadoop and Hausenblas is pretty neat and has a lot of advantages. So how would you explain that and what time tests every time?
That we don't find the central word?
Every time and everywhere.
Every time and everywhere? Oh, actually, Cassandra is used very much. We've got more than 250 commercial customers now with DataStax Enterprise, and the Cassandra is much more than that. I mean, it's very popular as that real-time as a component-based store. So yes, I don't have the slide with all the big names that I use in Cassandra.
Well, I think he already described kind of the zen of where Cassandra comes from. Is real-time, and so if you're coming from the standpoint of I want a really good real-time scalable store, you would use Cassandra, and then the reason why people don't use this particular solution rather than using one of the other Hadoop distributions is This is more from the perspective of I have all of this real-time large amounts of data, and I do want to run analytic jobs on it, rather than I'm coming at it from a purely analytic background. So there's kind of a little bit different starting point there, I guess. So people using it for purely analytic workloads may have no need for some kind of real-time data store. So a large number of people just use Hadoop on its own, vanilla Hadoop. So does that kind of answer your question? This is why it's not as pervasive in this form, I guess.
Which part? I mean, the DataStax Enterprise, it's not open source, but you can test it without any license fee. You just can grab it from the website, and until you launch it, you don't have to buy commercial support. Of course, you could actually do all that stuff, but you waste lots of time, yeah, for integrating it like that.
Because Cassandra obviously is open source.
Yes.
Yes. You added some extra bits.
So is the CFS something owned by DataStax or is it open source?
CFS? No, CFS is a part of the DataStax Enterprise platform. So this is that added bit. That's one thing.
One more question.
We should use Cassandra over HBase.
Cassandra over HBase. I think that Jeremy answered that very much. If you are mainly real-time focused, I mean that the main thing your application does is the very efficient handling workloads, then Cassandra is the way to go. If you're purely analytical focused and you, sometimes need to do some smart parts in, real-time, so then probably you're better off with Hadoop, standard Hadoop distribution and HBase on top of it. Okay, there are lots of benchmarks comparing HBase to Cassandra, and I recommend it.
Thank you very much.
My name is Jeremy Hanna. I work at DataStax as a support engineer. So people have problems with their clusters, and we try to handle them the best that we can. And so I talk to a lot of customers, and my background is I started working a few years ago on Hadoop. We had at Rackspace we had a shared services division where they didn't want to duplicate operations teams and so forth, and so we started doing some shared clusters for people who didn't have a huge need for Hadoop, but they didn't want to invest in the operational staff for each team. And so we did that for Hadoop, and then we did that. We started to add capabilities for that kind of thing, kind of multi-tenancy to Cassandra, and then Rackspace kind of decided that they didn't want to go in that direction. And so many of my team actually left, and one went to Twitter, a couple went to DataStax. So anyway, my background is kind of bridging that gap with Cassandra and Hadoop and the integration there. And so I've been doing that for a while. The most previous company I was at did social media analytics. So for, say, Nokia launches a new product and how the campaign is being received in terms of judging people's responses in Brazil. They wanted to find out how it was being received and how the conversation was going on Twitter, Facebook, and all that kind of stuff. So we used Cassandra for our data store, and we used Hadoop over that. And like I mentioned before, it was at the time there was no DataStax Enterprise. Apache Hadoop had just released 0.21, which was kind of a non-release of this is. It seemed to me at least it was kind of like here's a pipeline of changes. Let's put it in there. It's not production worthy because there wasn't really a maintainer. So back then we used CDH3 because it was well maintained and a lot of people relied on it alongside Cassandra. Anyway, so that's my background. What I'm talking about today is Hadoop with Cassandra best practices, and that being my background. And you can see you say the soul, the Cassandra logo is an eye, so I put that on that. I like that little combination. But I think it also highlights one other thing is that, like Piotr mentioned, we're coming at it from different directions. Google came at it from a direction of, okay, you have Google file system, a distributed file system, and then you did MapR jobs, which are batch analytic jobs in parallel. You're moving the processing to the data. That was kind of the magic there. And so it seems curious and fascinating to me that they then put a real-time data store on top of a purely batch-oriented system and relied on, very common techniques with cache. I'm not an expert on Bigtable or HBase, but it just seems fascinating to me that you have those two together. And so Cassandra comes at it from the standpoint of, okay, well, you have a real-time system, you have this large amount of data that's stored in a real-time store, and you want to add analytics. The foundation is a real-time store, and you can put analytics on top of that instead of the other way around. Some background. Let's see. So the Hadoop support in Cassandra started in around 2010. There's column family record reader and input format, output format, that kind of thing. All the way back then, back to Cassandra 0.6. And MapR and Pig works with any open source Hadoop version. And so, like I said, we were using Pig with CDH3 with Cassandra at the place that I came from. And that worked really well. We just co-located on the same nodes the task trackers and data nodes, and then the job tracker. I can see down here, the data locality with reading and writing to Cassandra on that side of it it implements the same interfaces as with HDFS. And so the job tracker has an idea of, okay, I want to process this data A through F. Well, that happens to be stored in rows A through F on this node, and so I'll set up processing over there. So the data locality is a big thing because that's kind of the magic of MapR. And then Hive is kind of a neatly integrated thing. And so that your answer to your question about open sourcing the Hive component, it's kind of hard because the meta store being stored in Cassandra and the auto mapping and things like that are kind of a nice convenience that are added on top of it. So data locality. And the other thing to note is that I think there's a difference in the implementations. I think HBase, they have the same similar data storage concepts, but you're limited, I think, and if somebody knows better than I do, please, on the order of maybe like a handful of column families, maybe up to like 20, 30, that range of number of column families. Whereas Cassandra, the overhead, there is some overhead, so we recommend customers staying within about 200 column families. So that's a property that helps decide later how you model things. So setting up the cluster, you can do this with open source Cassandra as well as with DataStax Enterprise. You have an analytics-specific data center, so it's a virtual data center that you want to dedicate to a specific workload. So you have the consistency levels are flexible with Cassandra, and so say you only wanted to restrict reads, for instance. Say Netflix uses Cassandra in North America, South America, and Europe. And they want to restrict reads to Europe for requests that come from Europe. And so they would use something like the consistency level, which is a form of the nodes within the local data center where the call is being initiated. And that would only read from nodes within that region or data center. A similar concept is that with an analytics dedicated data center, you use something like local forum, and it would take the reads only from that specific data center, so it wouldn't pollute the reads of any of the other data centers that were meant for real time. And so that's kind of the thinking behind the workload separation. And then, of course, if you have replicas in multiple data centers, those propagate out throughout the cluster. And as far as configuration, if you're familiar with the different best practices with Hadoop in terms of the number of task trackers and the amount of I/O that it takes and things, there's another component, which is Cassandra, which is the system as well. But with DataStax Enterprise, it's integrated with Cassandra. So the same characteristics generally apply. I mean, you have, Cassandra's not CPU heavy, and so you basically have the same resources in terms of task trackers, and then you also have your memory. With DataStax Enterprise, the task tracker and the job tracker are in the same heap as Cassandra, and then it forks the JVM to create the various tasks that are run, and so it has its own dedicated heap of memory. So same best practices. So it's not like you're in a completely separate world where you have to relearn all of the best practices in terms of configuration. So as Piotr mentioned, and as we did at my last job, we use vanilla heavy report, in that case CBH3. You just co-locate the task trackers and data nodes with Cassandra nodes. And that way you achieve the data locale we're looking for. And then similarly with DataStax Enterprise, you can configure a virtual data center to isolate the workloads within a single data center. So best practices in terms of planning. One of the trade-offs is that Cassandra, in order to avoid hotspots, uses a random partitioner where it takes a key and then does some sort of hash function on it, and then says where in the ring it will go. And so you don't have sequential by row key, you have sequential by column name. And so when you do a MapReduce over a column family, typically the common case is to MapReduce over the entire column family. And so you have to plan accordingly. And I think some of these NoSQL systems, you have to, there's a lot more planning involved, like for instance with the data model, because you're starting from day one not to think logic data, but in terms of the access pattern on top of the data. And so you model the data accordingly. So for instance, if you have a set of data that is the last 12 months of interactions on your website, and you might want to just have it in one column family, and logically it might fit in one column family, but in terms of doing MapReduce, if you have an archive that is constantly growing, and each time you want to run a MapReduce job over it, you're scanning the entire data of that column family. You know, it's going to take more time as time progresses. There's nothing magic there. So how do you get around that with running analytics on this data? One way to do that is to add more column families for specific purposes. It's kind of a different thinking of denormalization. You might have one each month, and perhaps a column family for your archival data, so the data exists all in one place, but in parallel you write it to maybe different column families represented by some logical construct, like the month of the year or something like that. And you can also use Cassandra's TTL support to TTL that data, so you could say, give me the last 30 days of the data and MapReduce only over that. If you use TTLs, you can do that as well. So you just kind of have to get a little more creative in your data modeling, and think try to think through the different things that you would like to do with it. You can use secondary indexes as a way to filter down the data, but you need to use caution. It's a scatter, gather, multi-get type of thing where it's like I said, it's a hash-based secondary index, and so what it does is it's column family with the value and then all of the keys that belong to that value. So Subaru and all of the cars, all of the instances of Subaru are in one row in the secondary index. So you're looking for high cardinality. And so when you use secondary indexes, what it does is it first gets the key and then it has to do the seek on each of the rows for that. And so in order to do a multi-get operation like that, you don't want to have large subsets of your data going through MapReduce. That's pretty inefficient to do multi-gets on all of those rows. So it's something to be used with caution. I work in support, and so I always have to keep in mind, okay, well, theoretically, that's a really neat concept, but in practice, that's you want to be careful. Okay, so that's planning, the planning section. Execution, I think this is similar. These are similar principles. Normal Hadoop is just project and select earlier in your workflow. For instance, we had a set of data which was all of the social data that we had collected for the past n time period, and we had scanned over the entire column family and narrowed it down at that point, and we worked on it multiple times, and so you just select and project, put it out to an intermediate spot, and then use that multiple times in your workflow. So that's one way to this is the best practices presentation. So that's kind of the best practice, is to narrow down your data sooner. And I think that's just a general computer science principle anyway. But store, like I said, store common intermediate data sets in CFS or HDFS. The bulk loader output format excels. I mean, you're just saying SS tables, go, 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 all to the different nodes, instead of using the client interface. And so that's really loaded to your cluster. And people may have the use case of, well, how am I going to bootstrap my Cassandra cluster? In fact, Op Center, the management tool represented earlier in Piotr's presentation, uses the bulk loader to restore data to your cluster. It just takes this huge directory of SS tables and then just shoots them out to all the nodes, and then voila, you have all of your data is restored within your cluster. And so it has some nice applications. So use cases, you have your typical Hadoop tasks for reporting, analytics, recommendation, like with Mahout and things like that. All of those typical use cases. Some things that I found were especially helpful with the integration with Cassandra were, I have a ton of data that I just inserted, and I found out somebody introduced a bug in some build that I don't know about, like, you know, over the last few days, that tags all of Beethoven's data as heavy metal, you know, something like that, where there's some kind of corruption in your data that isn't correct, and you want to quantify how much of your data has been affected. And so this might be a nice application to use to know the scope of the corruption in this case. And we did that. We had bugs in our code, and we had to go through and find out, not only validate it, but also fix it. You can use, like, you have this huge amount of data that's been denormalized, and you want to fix the things that were corrupted. And so you can use the Hadoop support to do that. And then one other thing that we found useful is, okay, well, we have a new access pattern. Cassandra's data model is very access pattern oriented. So you have all of the user's data in one column family, and you say, well, I want a column family that's just dedicated to demographics for the groups of, you know, the common age groups, you know, 15 to 25 and all the way up. Well, you can use the Hadoop support to read in all of the data from your user's column family, and then create bootstrap historical data for the age groups demographics data. So that's kind of a handy feature. And that's about it as far as best practices. I realize I should have done this presentation also in French, because my mother is a French teacher. She's ashamed of me right now. I speak Italian, but I never taught French now. And are there any questions?
In French.
In French.
Let's take 2 quick questions.
Sure. 2 quick questions.
My question is about the application. In the previous presentation, you write that you need to recreate the data on each node, is that right?
Oh, so you're wondering about the replication of the data that's stored in CFS?
Yeah.
Because in normal Hadoop, you set your replication factor for the HDFS. In Cassandra, with the Cassandra file system, it's exactly the same. It's just the replication factor of the key space, which is called CFS. And so you say, I want 3 copies of that data within these 10 nodes, which are in this analytics data center, and it will handle the rest. And in fact, you can have multiple CFS instances as well. Also, if you want to say, I want and have a different replication factor because it's very transitory data that I don't really care about that much, and I'll just have a replication factor of like 1 or 2 in that same. So it's key space and data center base is the replication factor. So you're asking if you need to re-replicate the data once it's gone through the processes with Cassandra? It's handled transparently underneath, so if you write it out to CFS, either in an intermediate way or within the job or at the end of the job, it will be replicated for you. And so, but I'm just wondering what. I'm sorry, I'm having a hard time hearing. Okay, you can ask me afterwards. Are there other questions? One more question? Cool, thank you.
Warm in here, but maybe you have another 5 or 10 minutes of your energy. My name is Michael Hausenblas. I'm a data engineer with MapR, based out in Ireland. And we started our EMEA operations end of last year. Now having offices all over Europe, Germany, UK, Paris, as mentioned. And I'm very glad that we already discussed some of the things here. Makes my life easier. So the way I see it, the reason why Hadoop will win long run is exactly that. So if you think about the 3 V's, no matter how popular they are, the relational database world really, you can see the relational database world really as a small corner case of the big data. Right? So as long as you have, small variety, essentially only relational, and a low velocity, you're pretty well off with relational databases. But as soon as you have a combination of these, you probably need something from the Hadoop ecosystem. So a question I typically ask the audience: what kind of workloads do you see in your environment, project, product, whatever? How about that? Thank you, Jack, for that. Anyone aware of or familiar with the Lambda architecture? Heard of that? Very good. You get a beer after. Nathan Marks of Twitter, former Twitter now, his own stuff, came up with that idea, wrote a very nice book on that, and I think it's worth it looking into that. And this batch processing could be used for the batch data. Proposed Lambda architecture. We have for OLTP or lightweight OLTP, we have HBase or Cassandra. There are a number of things. Facebook's website, for example, large-scale user, any kind of these messages, these and that could be, for example, used in the same layer of an environment. We have stream processing. There are a number of streams out there. Social media streams. You think of the IoT things, mobile phones, RFID chips, whatnot. We have a number of stream sources that to process, and that could, for example, be a speed layer or used in a speed layer of MapR. And of course, good old search and information retrieval. These 2 popular products based on Lucene, Doug over there has written initially. They are pretty much able to retrieve items from any kind of structured, semi-structured, unstructured sources, and getting more popular in most of the distributions, integrate them, relax. So thinking about what I just said about the different workloads, the question is, what does MapR actually do? And what we provide is a big data platform, processing platform, including Hadoop. And so typically you have your cluster here that could be on-site physical machines or in the cloud. AWS offerings, or Google Computer Engine, some kind of cluster. And you have the storage layer, and what we did initially, we started up in 2009, the first 2 years, we were in stealth mode, and essentially we wrote a distributed file system, and yes, that's what I did. And on top of that, you have, depending on the workload, depending on the needs of the application, you have different kinds of ways to address. So, for example, there are a number out there that want to directly talk to this file system as direct access. For batch processing, as earlier mentioned, MapReduce paradigm, OLTP covered by HBase M7, interactive query, Apache Drill, I must have forgotten that early on. Stream processing, Storm, for example, nicely integrated, and search, Solar or Elasticsearch. Recently announced a partnership with LucidWorks where we do this whole integration quite nice. And of course, the typical configuration and monitoring stuff you would expect as a DevOps in order to see how your cluster is doing or your application. First, I'm going to talk about HBase in M7. So the basic idea essentially is we looked at what do people use and where are their pain points in terms of. We found that a big amount of people actually use HBase, and that's for a number of different use cases and workloads. And that's probably also the same when I've talked with some people from their important works with other distributions. So we thought, okay, let's ask people what are the issues with it. What do you see in production usage? What kind of issues we experience? And we figured there is quite some things to be done. So grouped them in different categories in terms of reliability, business continuity, performance, and manageability. And that's one of the things that we take very serious in terms of enterprise-grade software for large-scale processing. Things like these three, marketing terms. It's easy, dependable, and fast. And if you look at what is provided, things like volumes and mirroring of snapshots, people are pretty used to that from their traditional settings when they have things like a volume or a snapshot or a mirroring functionality. And so how does it look like? How does M7 or HBase with M7 look like in our distribution? So you essentially have a kind of logical namespace here, or a unified namespace over both tables and files. So in the files area, you might use normal text files, or RC files, or whatnot in Hadoop. And in HBase, you have the tables. And what you see here is volumes. And the volume is essentially a logical way to partition your namespace, right? Do that based on users or a project where you have the production volume and so on. The nice thing about that is that on the volume level, you can apply things like the quota, doing snapshots really fast. It's a very simple and effective way to capture the current state of the file system. And of course, you can do mirroring on volume level. So that volume concept is something that you won't get in any other distribution. There you always have to talk about the end time. Right? You can do mirroring cross sites, customers that do mirroring across the Atlantic and so on. Just to give you an idea of how that looks on the command line, I recorded a shell session here. So, sometimes people don't get it, but things like that, you can't really do it directly with HBase and do it with M7. And it doesn't matter if you look here. The T here stands for essentially treat the tables in the same way you treat files. You can copy them. So that's the basic idea, having a unified namespace. And of course, directly interact with the HBase shell here, creating tables, manipulating tables. So how did we do that? Essentially, that is what you get with vanilla Apache Hadoop and a number of other distributions. So you have a kind of layering of these JVMs and so on. And with M3 and M5, that were the two previous revisions of our software, we essentially kill one of these layers. And the less layers you have, that's kind of obvious. The faster you get, the less dependencies you have, and the less things at the end of the day you get broken. And yeah, with M7, we essentially reduced it again and made it even faster. So just to give you a bit of an overview, we had very interesting Cassandra talks already, and what we did there, if you look at the compaction, and I don't know how many people are familiar with compaction issues around HBase. So what you essentially do there is, because HBase is layered on top of HDFS, and HDFS is end only, you need to, every now and then, if you have stuff in there that you don't need anymore, mark it as deleted, you need to clean up. It's like defragmentation in the local file. And this can take time, and it means that your cluster is essentially empty. And these kind of things are, at least in our customer base, we've identified that a huge pain, as long as you're, as soon as you're in production. As long as you're just toying around in the dev cluster, probably can deal with that if you have to shut it down for half a day. But if you're in production and you have SLAs, you need to, this kind of compaction issues is really big. So what we essentially did with M7, the core message here is essentially combined the best of two worlds, from HBase style, way of doing it, into the style. And one question we often get is, how is that in terms of portability? Is there a vendor login? No, that's one of the things we guarantee, both in terms of HBase and HBase. There is no vendor login, right? It's API compatible, and which means you can start out with another distribution and without recompilation, whatever, drop it in. Works in MapR or the other way around. And you use the standard topic table tool to copy a table from HBase to M7. If you're, due to whatever reason, don't want to run M7, you can use standard HBase. Second part, that's probably even closer related to the hack here, is a pretty exciting project called Apache Drill. Apache Drill is essentially realizing this interactive ad hoc query at scale in a community network. So, good old chap here wondering, how can we do interactive ad hoc query at scale? Well, what we currently have are these kind of systems, and as Doug already mentioned, you don't really want to ETL stuff out and in, right? You don't want to ETL stuff from HDFS into Teradata or whatever, and then query their interactive. That's fundamentally growth. And Hive, although there are announcements on Stinger that might increase the whole thing or get down the latency, actually doesn't really fit with it. So what we have is a number of as here, as Doug already mentioned, Cloudera product Hanna. And what I'm going to talk about is Apache Drill. And let's have a look at some use cases. So with Jane, she's a marketing analyst, and she has a deadline. As you know, with deadline was yesterday, and she has to come up with a new marketing campaign, determine certain target segments, essentially figuring out whom to send the ad. And she has the data spread over different data sources. For example, a relational database with transaction information. User profiles to pull kids to MongoDB, so they have to store there, and exit logs. So that's the challenge there, to integrate the data from different data sources. Another use case from the logistics area, imagine you need to supply, to track suppliers. So how are certain suppliers doing? And you might, again, have certain parts of the data in relation data, some other part in JSON. The actual shipment logs are here. And you have a very, and that's one of the things with these ad hoc queries, very important, a very specific set of queries. So you're not asking general questions, but very specific questions. The third one, again, comes from the real world, from one of our customers. Imagine that in the MapReduce batch file, you create such a heat map, and you are in this crime detection, fraud, whatever, business. And some human operator looks at that and can identify, ooh, something is going on there. But imagine that each of these pixels here might be 1,000 or 100,000 transactions. So you can just only say, there is something going on there, but in order to verify is that really fraudulent action, you need to drill it out. So you get a bit of a layer, but then you need a tool that allows you to drill it out. But this gives you already an idea of what questions, what types of questions to ask. Really. That's, to me, a very appealing use case for drill or other interface theory systems that work in kind of synergistic ways. So from these set of use cases, some requirements. We identified the need to support different kinds of data. We've seen could be still in relation databases, Mongo, HBase, Cassandra. We want to be able to support different kinds of query interfaces. Yes, SQL is important, and SQL should be supported, but there might be the need for domain-specific. Of course, it has to be low latency. I don't really like the term real-time so much. It very much depends on the system, what real-time means. So low latency here, with the human sitting in front of a computer, clicks on it and expects something back in reason. The talk queries is very important. Our knowledge about the data, what the requirements on it might change quite rapidly. So you need to be able to ask questions in advance. But of course, it's usually needs to be scalable and reliable. Bit of a backdrop here. Who of you knows Google Drive? Cool. I knew that. So in 2010, the Google engineers published this paper and highlighted some of the more interesting bits from the abstract here. Interactive, ad hoc, read-only nested data, and the two main innovations, multi-level distribution trees and so on. So what are these two main innovations they introduced there back in 2010? On the one hand, the idea of you have a distributed file staircase, HBase well. And if you can do these queries or these scans in parallel, then you're probably faster getting a result. The base assumption here is that the stuff you send up there, the result set, is relatively speaking to the overall input data set rather tiny, right? So in contrast to MapReduce, where you potentially the output data set size might be in the same dimension as the input, bigger. Here we really assume that the result data set size is compared tiny, right? If you have rows, you divide it. That's right. And the second innovation there is these column-oriented formats. So essentially the idea of storing tabular data column-wise, that has been around for quite a while. Relation database for 20 years. But the problem of mapping nested data, so in their case protocol buffers, the Hadoop ecosystem, you might talk about Avro, Grid, you might talk about JSON as well. Very funny. So what they did essentially is they came up with an algorithm to map these nested data structures into tabular and then you can apply these questions. And they also did some experiments around that and essentially showed that it's, yeah, you can have quite some improvement using these two techniques to grade. So obviously we're inspired by grammar, so is Hanna, I take it. What we have is standard SQL 2003 support that's based out of contributor with height, and tau, source library that he essentially adapted or contributes to drill. If you remember the requirements, pluggable data sources, that's really essential for us. We can come up with a new data store, a data store that is not yet provided by ourselves. We can do that, we can extend that. We treat nested data as first-class citizens, having that mapping done automatically. The schema is optional. If you don't have a schema, quite often the case, we try our best to explore it based on data. And to me, the most important thing, because it's not only open source, open source license, and Apache project, means community driven. And I give this talk quite often. To me, the major thing with this Apache project is that people in the audience have an influence. And influence in many ways. I'll talk to that later again. But that's the main thing to me. The community decides, and if you think back, why at the end of the day was HBase and so on very successful? Well, because different people with different backgrounds, even competitors, who come together and agree upon the interface, right? The API, and then you can provide better implementations. So, from a very high-level point of view, what you have in Drill is you have data sources, as I said, pluggable. I'll come to that in a second, and then you have pretty much the standard APIs, interfaces that you would expect there. REST API, command line interface, share with, interact with it, native API, script in Java, and JDBC, ODBC. Number of terms here that we use internally for different things there. Source query essentially tells you what you want to do. The logical plan we came up with that says in an agnostic way what you want to do. The physical plan that essentially tells you how you want to do things. Plan what distributed setup you might want to know where you want to do things. And that's how it works. So you get in, let's say, SQL, could be something else, monocular, or in specific language. A parser translates that into logical plan, and that pretty much looks like JSON. Like, if you serialize it, you want for debug purpose, you want to serialize it, it is JSON. The optimizer, and those of you who are kind of in the background in relational databases might know what an optimizer does, translates this logical plan into a physical plan that takes into account a number of things, topology, components, or use. Then you have the execution that depends on the scanner API against whatever the data stores, different data stores. On the while level architecture, so we have, let's say, a 4-node cluster. On each of the node a little bit, even running the storage process, knows how to talk with the rest of the data stores. And it will be pretty much the same idea as with MapReduce. We want to leverage the data. We want to send the code over where the data is again. Should be data around, as we mentioned. And everything else there, coordination, query planning, execution, and so on, in fact, distributed. How does it work? Well, we use Zookeeper, very surprisingly, but we only use the network security package, which is wrapped around Zookeeper. Zookeeper is not really that easy to use. If you want something that has with a higher level abstraction there, and we use a distributed cache, called Hausenblas. Zookeeper essentially is used for the membership information, so which node is up, data, and so on. And the distributed cache is used for the metadata. It's very similar. So what happens here is, if you take this one, someone sends in a query, and you can really take any of these nodes, sends in the query to this one. This little bit then gets what we call a format, turns into a format, driving the entire query. And what we're doing there, we really try to avoid as much as possible any kind of writing to disk, writing to memory, and again, that works because the data results in size small. I think what MapReduce, you always would go to the FIO to the disk, and again in the Java phase, go to network, and then again in the reduce, you would always go to disk. So this little bit is becoming the format. If you think back to the Dremel backdrop I gave you, we have this multi-level execution tree, and the root of this multi-level execution tree distributes the query over down to the workers. They actually do the work. They have the storage process, scan the respective part, and then report back results. That's the formula that sends the result to the file. And of course, we are standing on shoulders of giants. There are a number of things we're using here. Yeah, as you can see, a number of libraries and so on, and so on. we essentially reuse rather than reinvent. Some of the key features of Apache Drill, as I said, full SQL 2003, nested data as first-class citizens, optional schema, and extensibility points. The extensibility points, to be honest, that's what to me is the most important. Because it means that at any point here, the logical plan, physical plan, whatever, is your own way of doing things. For example, you can come up with custom operators, using defined functions, with your own optimizer, any kind of data source, data formats you want to support your approach, or you want to use your approach. That's to me is the key to Apache. I often get the question, how is it with Hadoop? Is that these interactive query things are taking over Hadoop? No, it's not. It's a complementary thing, and the Google developer have put together a very nice white paper on that. Have a look at that. Essentially taking care of BigQuery, which is the service offering of Gremlin with the stuff, a number of use cases. So let's have a look at that. This basic demo is already around for quite a while. It essentially shows how you can use a JSON input with a simple logical plan. Wrote by hand, which is not very funny. Now we have a smart code and a SQL parser, and this gets generated automatically. And if you run this through Drill in a single node, you get out. That's not very sexy, it's just a single node, and that's what we're currently working on, having the distributed setup in a zero configuration available next couple of weeks. So you can play around. Just download it and run the shells. So how does it look like? If you look at the source query here, as you can see here, actually, technically, it's an extension. So in order to address the nested data structure, you need to have some construct to be able to address the subfields. So that's more this. That source query gets translated into the logical plan by the SQL parser, is already more or less fully available. One issues the last time. And then gets the translate plan that then essentially has really the low-level things. There's some push down. We try to push down as much as we can. Data source. Because the assumption is that the data source, like a relation database, knows better how to query things than we can. And the execution plan then takes this into different fragments and tries to parallelize that as much as possible. And as I said, to me, the most important thing to me is be part of it. So currently we have development, a number of things are already available. Mentioned already, SQL support, SQL plan is there, and this one is really the tricky bit to get that right in some sense. We have HBase in MySQL, and as I already mentioned earlier, different user interfaces, and there we're doing pretty well. And if I would stop wandering around and talk about that, I would probably get back to that last year and more adapted to different infrastructure, of course, So, the question quite often is, can I only contribute if I'm a coder? The good news is no, you can also be not a coder. For example, if you have use case scenarios, you say, oh, I really want to use Drill for this and this. You describe it in your own words, that's very much appreciated. Or come up with test data, test queries, documentation, whatever. So everyone can really help or shape this. Shout-outs to my colleagues out there that have been so far mainly contributing to the effort, and many more. I think there are over 300 people on the mailing list. And last but not least, engage. So you can, depending on what you want to do, you can follow us on Twitter. You can sign a development list. Every Tuesday at 6, we have this Google Plus hangout. We together report on progress. And if you're interested in it, then just tune in. We have been there over a week or second, even an existing event. Progress by and large. I think that pretty much made it in time, I hope. Yes? Yeah. We have some minutes? Yeah. Okay, cool. Then looking forward to questions.
used by MapR, and you write up and there are
So, I'm not going to answer the question regarding Cloudera. Doug can do it. I doubt it, though. It probably will be shipped by Hanna.
The question?
So the question was, will be part of distributions in general, MapR and others. So, as I said, in MapR case, going back to this, I'm going to share these slides after anyways. So in this case, this is the workload, and of course we are one of the core contributors to Apache Drill, which means we will integrate that. If someone, the customer says, "Oh, yeah, we want to do it in color," that's awesome. So from our point of view, we take whatever open source or not so open source component is out there from the ecosystem, are very driven by the customer. If the customer wants it, to make sure that we integrate it, run it through QA, and make sure that it's available, patched, and usable for the customer. But I can't talk. I pretty much, my hunch is, MapR mainly sponsors and puts engineering resources into Apache Drill. Cloudera obviously in Impala, and workloads, as far as I understand, potentially behind the Singer initiative, potentially high fast. That's roughly what the situation. But maybe Dr. has other ones like other ideas there. I would love to hear other opinions on that. Or over a year, maybe it's less pressure. Sorry, do we have more questions?
I think people are hungry.
People are hungry and it's late. Okay. Thank you very much.